I would like to share about our block diagram. So we have hardware component and we have power source. So we have 3 input and 3 output. First, our input is power source and sensor and resistor, and our output is servo motor, LED and buzzer. So the piezoelectric sensor detect the vibration of car and send message to embed, and the embed process that information and then send to our output, which is LED and buzzer. Okay, next is our circuit diagram. Okay, firstly, our piezoelectric sensor connect to pin number 15, and if you can see, our buzzer connect to pin number 2, and another polarity which is negative connect to NPN transistor collector. Okay, next our resistor connect to pin 25 and base NPN transistor, and our emitter NPN connect to the ground. And last but not least, our servo motor, we have 3 pin, which is V-in, digital and ground. So V-in, we connect to the VCC, and digital we connect to pin number 26, and lastly is ground, connect to the ground. So lastly, this is our hardware we were able to build. So we only had time to do wiring, connect all the components and setting up our coding on LPC board. That's all.
Assalamualaikum dan selamat sejahtera. My name is Ahmad Lutfi bin Nosham, and I'll be showing you the process on how to configure the ADC module, the analog input pins, converting the analog to digital output, and also setting the threshold for the analog input. On configuring the ADC module, step 1, we need to enable the power for the ADC module. So this is the address for the ADC module, and then we set the value 1 to bit 12 and the hexadecimal as follows. Then we need to let the ADC module to be operational. So here's the address for the AD0CR, and we're going to set value 1 to bit 21, so the hexadecimals as follows. Then step 3, we need to enable the peripheral clock for the ADC module. So here is the address for PSCK cell 0, and then we need to set bit 25 and 24 as value 1, and the hexadecimal as follows. And then step 4, we need to set the analog pins. So since we are using pin 19, so we're going to set pin cell 3, and the address is as follows. And pin cell 3 is P 1.3, so we need to set value 1 on bit 29 and 28. So the hexadecimals will be as follows. And then step 5, we need to select the respective analog pin for the analog to digital conversion. So we already set up the AD0CR, so we just need to load it. And since we are using pin 19, which is P1.3 and AD0.4, we need to add 1 on the 4th, the value 1 on the 4th bit, so that the hexadecimal will be as follows on line 45. And finally, we need to set up the register for AD0 GDR to isolate and convert the value from analog to digital. So here's the main body of the coding. So on starting the analog to digital conversion on pin 19, we need to first load the AD0CR, which already stated above. Then to start the conversion value, we need to set 001 bit on bit 26 to 24, and the hexadecimal will be as follows. And then we store the value. Then to read the converted value, we need to load the AD0 GDR for isolation. So to isolate the values that is converted, you need to make bit 15 to 4 as FFF, so the values are stored there. And finally, you can set the input threshold for the piezo. So the threshold can be set in R0, and then we can compare R0 to R7, which is the stored value. And finally, we can proceed with the next program. If the comparison of R7 is less than the compared value, then we will start over from the top on line 53.
Next, we have the coding of Supermoto in assembly language. In this project, Supermoto will act as bumper to reduce the speed of car. First, we have L call 0 degrees, where it is to move to position 0 degree, where the Supermoto will not rotate. Next, we have L call delay to create a delay of 1 second. Next, we have L call 90 degrees, where it is to move to position 90 degree, where the Supermoto will rotate in 90 degree. Next, we have L call delay. It is to create a delay of 1 second. For 0 degrees, we using timer 0 in mode 1, where TH0 and TL0 are set in such a way that we get 1000 microsecond delay. The timer counts up from whatever value we give. If the initial value is 0000, then timer move from 0000 to FFFF, and an extra transition from FFF to 0000 before the flag TF0 is set. Set B P26 are used because we connect the connection from Supermoto to P26 of embed. It is to make P26 high. Then set B TR0, it is to start the timer 0. We wait till the TF0 flag, then we will clear P26, which is to make P26 low. Then we clear TF0, where the flag will clear manually. Then we will stop the timer 0. To generate a pulse of 1.5 millisecond equal to 1500 microsecond corresponding to 90 degrees, we use TH0 equal to FAH and TL0 equal to 25H. Then, same as at 0 degree, we set P26 to make P26 higher. Then set BTR0, it is to start the timer 0. Then we wait till the TF0 flag is set. Then we will clear P26 to make P26 low. After that, we clear the flag manually and stop the timer to 0. To generate a delay of 1 second corresponding to the wait time between this position, we use the DJNZ command with nested loop, creating a delay of 100 microsecond times 100 microsecond times 100 microsecond equal to 1 second.
This is the coding for buzzer output. IO1 DIR is a direction register where the direction of the particular port will be mentioned over here, which is port 1. IO1 DIR is a unique memory address. In the beginning of the program, we have to initialize this one. Whenever I'm using IO1 DIR, it will be replaced with this memory address. 1 means that particular pin will behave as an output port. IO1 set is a register where I can set in the content. In IO1 clear, whatever bit I am putting as the value 1, that particular bit will be reset. For IO1P is where I'm putting the value as 1 in the particular port pin, we will get it as 1. And if I'm putting the value 0 in the particular port pin, we will get it as 0. This 3 line does a single job of initializing the port 1 register as an output port. Next, load R2 from the address in IO1 set, then store R2 to R1, then BL delay, which is equals to delay this, which is then BL delay, which is equals to delay part. In this delay loop, load this memory address to R4. SUB means subtract. S represents set the flag register, which means change the flag register according to the arithmetic operation that was performed. For this line, it means that the content of R4 will be subtract with 1. BNEL means branch if not equal, so it is 0 flag. If R4 has not become 0, this will subtract again and again until R4 becomes 0. When R4 becomes 0, it comes out from this delay loop and it goes to instruction over here. Load R3 from address in IO1 clear, then store R3 to R1, then it goes to delay loop again until it's executed and this program.